Hello everyone, today we will be talking about my homemade Taser 3.0 with even more improvements compared to the last version. And as you can see, that it's got batteries this time, so we don't have to rely on this dinky pack of supercapacitors anymore. That's out of the picture. Now we have two 14500 size lithium-ion batteries, which are AA size, but it's a lithium-ion battery instead of a alkaline or nickel metal hydride or zinc carbon battery. And I also have put a fusion series because these batteries can deliver plenty of juice, and if they deliver too much juice, they get quite a bit excited and start to go into something called thermal runaway, which will cause them to build up pressure inside and release flammable gas out the top, which is nice, but at least these are the style that are in a metal housing. The pouch-style batteries are even worse because they will puff up and release a giant cloud of smoke. And these are also quite small batteries, around 300 milliamp hours apiece, and it's probably going to be even less, but you only use a taser for small intervals of time when you're shocking people, so it's not really that big of a deal that they're low capacity. And of course, when I turn it on and press the button, the neon indicator lights up to indicate the high voltage. I am not going to shock myself with this, and you will see why soon. Here's the clamp meter. Let's set it to 600 volts, change it to AC, and use alligator clips to hook up the probes to the wires, because I really don't want to hold both wires with the same hand, and I'm fine with touching one wire, it's just I can't touch both. So let's hold it like that. Make sure that it's properly propped up, and turn the power on, and tase. 82 volts! That is quite a lot for what I have over here, which is just a relay switching a transformer. And that 80 volts is quite significant, especially since that's the average voltage, or the RMS voltage, and the peak voltage the peak-to-peak voltage is going to be a lot higher than that. So I really don't want to shock myself with this. And the reason that it's so much stronger compared to before is because I have completely removed the resistor, limiting the current into the transformer, so now it has the ability to build up a lot more energy in the transformer core before it switches, and it hurts like crazy. And speaking of the driver, let's go ahead and look at some of the iterations that I've gone through. Get out. This is the first version of the Taser driver, which worked perfectly fine, even after I removed the current limiting resistor and replaced it with just a straight wire. But when I connected a resonant capacitor across the transformer, I think something died, and besides, the MOSFET was suffering from metal fatigue and ended up falling off, and because of my crappy soldering iron and crappy solder, I wasn't able to solder it back on. So now, or next, I should say, I built this driver, which has already had most of the components taken off of it because I needed them for other projects, including the modern version of the Taser. And it didn't work at all because I had used a BJT transistor, while on the previous one I had used a MOSFET. And the reason the BJT transistor didn't work is because in order for it to pass a specific amount of current between the collector and emitter, it has to have a specific amount of current going into the base. And it tried drawing too much current from the 555 timer, which would cause it to stop oscillating, and that would absolutely ruin it. And it also doesn't help that even if I try to limit the current into the base, it can't pass enough current between the collector and emitter, so the relay doesn't switch anymore. Or it does switch, but when I actually press the button to cause it to tase, then it suddenly stops switching. So then I made a third version of it, which hasn't been stripped down for components yet. And I put two of these same BJT transistors, wired them up in series, I guess, to form a Darlington pair, and I thought that because the Darlington pair only allows a small fraction of the current going into the base to pass the same amount of current from collector to emitter, it didn't work. I am not sure why, but it didn't work. But when I touched the input of this thing, I heard the relay switch at 60 Hz, and I realized, hey, why use a 555 oscillator to generate the frequency to switch the relay when I have all of the 60 Hz power lines around me radiating a perfectly fine frequency that I can use? So I came to the driver that was inside this thing now. Let me go take it apart. Where's the screwdriver? Alright, so here it is, and I have wired a, what I like to call a Trilington configuration, because a Darlington has 2 transistors, and this has 3, so I decided 3 is better than 2, so, I would use 3 transistors, but it didn't work, and then I realized that I was being an idiot this entire time, ever since that I first, thought of the idea of this first, driver. Because the relay can, oscillate on its own without any other components, and so I wired it up to do that, and it did just that. It oscillated, but it oscillated at a slightly too high frequency, so I added a capacitor across the coil to reduce that frequency, and now it switches at about 55 hertz, which is perfect. So, now I am going to put this thing back into the taser so that it will work again, but you probably don't want to see me do that. I have put the driver back into the box. It is sitting on a little piece of foam because this is a metal case and I don't want the bare solder connections on the bottom scratching through the metal and shorting out. And you might also notice that there is some white residue in this box that has actually leaked out a bit, and there is similar white residue on the top of this where it went together like this. This case came from an old refractometer, and it had a Duracell 9-volt battery inside of it that must have exploded at some point, and it busted all over the inside of this box. And after the bust had dried out, it left this white residue, which still remains here today, and it continues to eat away at the paint on the metal. And as you can see, there is quite a significant difference between the fresh paint and the busted paint. Anyway, let's get this thing back together. Also, I have to mention that in order to get these wires out of the box, I have to pass them through these 2 holes in the top part of the case, which is an extremely fun process, so let me go ahead and do that off camera. Alright, it's all back together now, and oh, sorry. Alright, it's all back together now, and let's go ahead and measure the voltage and current in the oscilloscope. So I have connected up Owen's probe directly to the output of this transformer, and the probe, or the oscilloscope, is on X10, and I will go ahead and set it on X1, so that way it should, the probe is still on X10, but the oscilloscope's on X1, so the oscilloscope should see 1/10 of the voltage that it expects. So let's go ahead and turn it on. And there's already some weird switching going on from the interference that the relay is generating, but when I press the button, it goes crazy. But anyway, here is the output waveform, which I have paused, of course, just so that you don't have to listen to that annoying sound. The peak voltage is 50 volts, and if we multiply that by 10, that means that it's around 500 volts peak. I hope you can understand why I didn't want to touch this thing. The frequency is 56 hertz, so right smack dab in the middle between European and North American mains voltage frequencies. And these giant spikes over here are, of course, from the inductor switching off, or the transformer current suddenly falling to 0, which of course causes a reverse voltage spike. And yeah, it's pretty crazy, but yeah, that's how it is. And that, of course, is the voltage across the output. But now, let's go ahead and remove this fuse over here, and instead of the fuse, hook up a 1 ohm resistor, like so, and now I can measure the voltage across it using the multimeter. Let's set it up to 20 volts, and of course my fuse is rolling away. It's on 20 volts, and now let's go ahead and turn the thing on, and measure the voltage across it, using a single hand, of course. And it doesn't show anything because the current is very low when only the relay is switching, so now I have to press the button in order to get the actual current flowing. Oh, come on, why aren't you working? Can't see the LED, or the neon indicator, I should say. Let's do that again. You can't see the current, but it appears to be about 600 milliamps. And let's try to get everything in a way that you can actually see the current. Hold on. Whatever, just take my word for it. The current was 60 milliamps, and you might wonder why why I was still able to measure current when I was on the voltage setting on this, and I could, of course, try to do this, but that's just going to measure the AC current, and I want to measure the DC current, and the DC current was 60 milliamps. This is a 1 ohm resistor, so the value that you would actually read here would be in amps, and it is 0.6, so that would be 600 milliamps. Now let's go ahead and hook up the oscilloscope to it, because I feel like we're going to see some much more interesting things hooking up the oscilloscope to it, because this isn't a pure DC signal, the current is constantly changing. And let's go ahead and hook up the oscilloscope, and of course unpause it, reset, and turn the thing on. Maybe put the probe on X1 instead to amplify the voltage, and of course you did see something, but the probe disconnected, so let's go ahead and zoom in. Alright. These are the current spikes from when the transformer isn't switching, and these happen because the relay has a coil in it, and when that coil switches, it draws some current, and of course, whenever it draws current, there's a spike on the meter. So these are about 2.3 volts peak, so it actually draws about 2.3 amps immediately when the relay switches, but because these pulses are very short, the fuse doesn't have enough time to heat up and blow open. And in fact, let's go ahead and try to measure the duration of those pulses. Here is the pulse. Let's go ahead and put the cursor on the time mode to measure the distance between the maximum peak, and the entire pulse lasts for about 0.88 milliseconds, or 880 microseconds, and the actual high current part of the pulse, where it actually exceeds 1 amp, is just 114 milliseconds, and a typical glass fuse like this isn't going to blow in 114 microseconds, so it's perfectly fine, because the average current is still very low, and you could tell because I wasn't able to measure it on the current meter, which of course only measures the average current. So let's go ahead and measure the current when it is in operation. So as you can see, it's quite a bit different. This slope that you get over here is the characteristic slope of an inductor building up a magnetic field in its core, and as soon as it switches off, it would produce a high voltage spike, which you don't see over here because I don't have channel 1 connected to measure the output. But as you can see, the average current is a lot higher. It's not just these little pulses of the inductor, it's this giant slope that you see over here, which is about half an amp, probably a little more than half an amp. So it still isn't enough to blow this fuse, but it is a lot closer to the limit of the fuse, which is probably a good thing, because if these lithium-ion batteries, if too much current is drawn from them, of course they will go into thermal runaway because they get too hot from their internal resistance. Anyway, that's about it for my homemade taser.